Hello, my name is Daniel Hudson, and I am presenting the Physics 2211 Lab 4. Some fundamental physics principles associated with this lab are Newton's second law, which states that final velocity is dependent on net force over mass times change in time, and the momentum principle, which states that change in momentum over change in time is equal to the net force. Basically, that net force has an impact on the object's velocity. We also use the conservation of energy, which states that within a closed system, the change in total energy will be equal to 0. For my experimental setup, I analyzed a video of a mass on a spring using Tracker. This mass was released and moved in a rough circle, depending on gravitational and spring potential energies. I then created a computational model of ideal movement and compared the two. So some observations I made, which I will get into later, is that there is no change in overall energy within the model, which insinuates that we have a closed system, and that gravitational energy is inversely proportional to spring potential energy. For my computational model, I used some calculations, some numbers that I calculated from data in Tracker to calculate Hooke's law, which is the spring potential energy, initial position and velocity, and gravitational potential energy to calculate the net force and motion of an object. Here is my GlowScript code, which I filled in data from Tracker and my own equations that I derived into this code. I calculate spring potential energy and the length of the relaxed spring using some oscillation data from Tracker. I also calculate the kinetic potential and different potential energies on the ball and a starting total energy. From there, I calculated all the forces on the spring all the forces on the object and the net force, and use that to calculate the ball's position and velocity. After running my computational model, I had these graphs which compared the model's position to the experiment's position. As we can see, the model overpredicts the object's position in both the x and y direction. Some reasons for this could be that the model does not account for all the net forces on the object, such as friction or air resistance, which could slow the object down and prevent it from reaching the same positions as the model. Additionally, I might not have been quite as precise while tracking my data in Tracker, which led to some of the discrepancies. So the energy principle is satisfied. The energy principle states that within a closed system, the total energy is equal to 0. As we can see in our graph down here, the orange line never wavers, is always at 0. The change in the delta U due to the gravitational potential energy and due to the spring potential energy are always inversely proportional, and with the kinetic energy they always cancel out to 0. So here we can say that no energy is lost to the surroundings. However, within the experiment, rather than the model, there may have been some energy lost to the surroundings due to air resistance or drag or something like that, and that could account for why the position isn't quite as accurate. Finally, I have the oscillations periods I calculated for both the x and y position. I calculate these by taking the time in between extremes on Tracker. As we can see, the x position is slightly longer than the y position. I took this to mean that the particle must not have been moving in an exact circle and must have been slightly ellipse-shaped and elongated more in the x direction than the y direction. There could also be some discrepancies due to the inaccuracy of my position tracking within Tracker. Thank you for listening to my Lab 4 video report.